Hello, my name is Will Klieber, and today I will talk about combined analysis of source code and binary code for software assurance. The goal of this project is to increase assurance of components that are available only in binary form. To do this, we will decompile the binary and then perform static analysis on the decompiled code. In some cases, we will even be able to perform localized repairs on some of the decompiled functions. Our ultimate goal is to increase trustworthiness of software that is fielded by the DoD. We are adapting an existing open source decompiler, Ghidra, to produce code that is suitable for static analysis and repair. So originally, Ghidra, as well as other existing decompilers, they were originally developed for aiding manual reverse engineering. They were not designed to produce recompilable code. So there is a gap. And the gap is that the decompiled code produced by these decompilers has semantic inaccuracies as well as syntactic errors. The key steps of this project are, first, to determine which functions of the binary have been correctly decompiled. Then we will run static analysis and localized repair on those correctly decompiled functions. And finally, we will recombine the repaired functions into the original binary. And there are existing tools that we can use to do this, such as disassemble. So a key insight behind this project is that a perfect decompilation of the entire binary is not necessary, as long as we can decompile enough relevant functions. The main contributions of this work are, first, to develop a semantic equivalence checker to determine which functions have been correctly decompiled. We are also improving the decompiler in order to produce better code for this project, code that has fewer semantic errors as well as syntactic errors. And we will submit these patches to the decompiler back to the mainline branch of Ghidra, which is used by other DoD organizations. So this line of work is continuing this year, FY22. This work will enable the DoD to find and fix potential vulnerabilities in binary code that might otherwise be cost-prohibitive to investigate or repair manually. And this will enable DoD to increase the trustworthiness of software that is fielded. We have collaborators and interested transition partners at the DoD, and they have binaries for which they want to increase software assurance. And they will work with us to evaluate and improve our tool, as well as use the tool in practice once it is ready. Here we see an example of original code and the corresponding decompiled code. So highlighted in yellow, you can see that the type of the first parameter is different in the original code and the decompiled code. In the original code, it is a pointer, that is what the asterisk indicates, whereas in the decompiled code, it is a long integer. And that is a discrepancy between the source code. In the binary, those have the same representation, so that is something that this project needs to deal with, and that is something that we are able to successfully deal with. So last year, a paper was published on testing the decompilation correctness of C decompilers. The authors of that paper tested synthetic code that did not have any input or non-determinism, and because of that, they were able to test semantic equivalence very easily. You just run the original program, run the decompiled program, and check that the output is the same. And because there's no input or non-determinism, you only need to do that once per program. So in the experiments in that paper, Ghidra was able to correctly decompile 93% of the test cases. However, there is a caveat to that, which is that paper investigated only unoptimized code with no structs, unions, arrays, or pointers. So here we see the pipeline that we're using in this project. We take the original binary, run it through the decompiler, get decompiled code, and then recompile that decompiled code. We then check whether the recompiled code, whether each function of the recompiled code, whether it is semantically equivalent to the corresponding function in the original binary. We then discard the functions that were incorrectly decompiled, and we pass along only those functions that were correctly decompiled for analysis and repair. So the previous pipeline is what we would use for when we actually use this tool in practice, but for measurement and evaluation, we are using a slightly different pipeline. We start with the original source code so that we have a source of ground truth, and then we take that original source code, run it through Clang to get a binary, decompile that binary, and then translate the decompiled code to LLVM intermediate representation, IR. We then check whether that LLVM IR is semantically equivalent to the LLVM IR we get from directly translating the original source code. We are using the Seahorn verification framework as the backend for our semantic equivalence checker. Seahorn, in turn, uses the Z3 SMT solver. We ask Seahorn, does the decompiled function have the same effect on memory as the original function? That is, we ask whether, for an arbitrary initial memory state, the decompiled function produces the same final memory state as the original function. So conceptually, we need to consider the entire memory space. But we can get by with using a representation of memory that is much smaller. And the way that we get that smaller representation is to have only one symbolic memory address for each memory access. So the SMT solver, because of that, the SMT solver must consider, it must explicitly consider aliasing between different symbolic addresses. So if you read from one symbolic address, the SMT solver must consider different symbolic addresses that are aliases of it. So this work is in progress, and we expect to have results early in FY22. This table shows the percentage of source code functions that are extracted as syntactically valid C code. And the way that we check that they are syntactically valid is by recompiling them. If they successfully recompile, that means they are syntactically valid. So we checked several programs from the SPEC 2006 benchmark suite, as well as a couple of other real-world programs, Git and FFmpeg. So as you can see in the table, around half of the functions were able to be successfully recompiled. Here we see a count of the types of syntactic errors that we encountered. The largest category are an incorrect number of functions to the argument, too few arguments, as well as too many arguments. So how do we fix the number of arguments to the function to get rid of those syntactic errors? Well, to make clearer what's happening, let's consider a chain of function calls. So let's say that we have one function fn1 that calls another function fn2, which in turn calls fn3. So on x86, the calling convention is that arguments are passed in CPU registers. And because of that, note that fn2 can forward some of its arguments to fn3 implicitly. That is, suppose that fn2 receives an argument in a register, and fn3 wants the same argument in the same register. In that case, fn2 does not need to execute any commands in order to pass that argument to fn3. It just leaves it in the same register that fn3 wants it. So because of that, we cannot determine the number of arguments of a function just by analyzing its own code as well as its caller's code. Instead, we might need to descend the entire chain of functions to analyze the function at the bottom. So what we do is we are going to do a whole program analysis. We will start by analyzing the leaf functions and work upwards, asking Ghidra to redo analysis giving the new information about the callees. And for recursive functions, we will use a fixed point algorithm. So in conclusion, we are adapting Ghidra to produce code that is suitable for static analysis and repair. So far, around half of the decompiled functions successfully recompile. We have not assessed semantic equivalence yet, but we should have preliminary results soon. And even if we are not able to get more than half of the functions to correctly recompile, that's okay, because we do not need a perfect decompilation. We can just do static analysis and repair on those functions that do successfully decompile, and that will still give a major benefit versus doing nothing. So this line of work is continuing this year, FY22. If you're interested in collaborating with us or in transitioning this work into practice, please get in touch with us. Thank you for your time.